Hello. So today I will be going absolute how to find absolute how to find local minimums, local maximums, saddle points with the second partial test. So the main thing that's going to help us to find the all of this is called the determinant. The determinant has a certain function to it, has a certain formula to it. The proof of it is very long, and I'm going to be honest, I still don't truthfully feel comfortable. I don't feel comfortable trying to explain it because I don't really understand it overall. But this determinant gives us the formula to find those things. Okay, so the determinant formula is the d is equal to the f partial derivative. Okay, so this is another notation for partial derivatives. It's just the f is the function you're respecting to, and then this is that you're deriving, and then the x is what you're doing in respect to. And if you see two x's, that means you're doing the double derivative of a and b, f, y, and y of a and b minus f, x, and y of a and b. All of that is squared. So we need to take the many derivatives here, many partials here. But the first thing we want to do, we want to find the critical points. So the critical points. So how do we find the critical points? Well, the critical points, if you remember, you just take the partial derivative, you just take the derivative and set equal to 0. So here's the same concept, except we're doing it with partials. So if we do the partial of f with respect to x, we will get, for this function, we will get negative 6x to the second, and we'll get 5y. Then we will get, yeah, that's it. And then we can set equal to 0. And right now it's really hard to tell what it is. So because of that, we're gonna have to do a system of equations. So we can do partial of f with respect to y, and that's equal to okay, so here everything is constant, so we just have 5x minus 6y. That's it. Okay, so we can set it equal to 0 also. So let's see what function. So to figure this out, we need to do a system of equations. So we can let's do maybe substitution. Substitution might be our best method here. So we isolate everything here. We have 5x, 6y, and then we divide this, and then we have y equals 5x over 6. Yep, and then we can substitute this thing into here, and then everything will be in terms of x's. So negative 6x squared plus 5 times 5, because we're going to substitute it. So 25 over 6x equal to 0. So in here, we can actually factor out an x of negative 6x plus 25 over 6. So one of our critical points the x will definitely have a 0, and then we can actually solve for it. So if we plug 0, right, 0 right here, this will give us this value. That means y is 0. So one of our points could be 0, 0. It's 0, 0, one of our critical points. Okay, so that's good. So now let's figure out the other x, because you see we have another x. So we take 25 to the other side, so we have negative 25 over 6 minus 6x. So now if we solve for x, we're going to have a value of 25 over 36. Which, yep, that's correct. Which is another x. 25 over 36. Okay, so let's plug it into here again. We could plug into here again. We could plug into any. I'm just choosing this one just because I think it will be easier. So we can do 5 times 25 over 36 minus 6y. We can figure out another y. So if we put this into a calculator, so 5 times 25 over 36, we're going to get a decimal, and we can put it in the other side right away. Negative 125 over 36 over 6y, and then we can figure out our y is actually 125 over 216. So we can plug that into here. So 125, not very nice numbers, but they're critical points. So these are our critical points. So these are the points that we're going to test out. And remember, because it's a three-dimensional, we're in two-dimensional space, you can have a point that's like this or like this, like single variable calculus. But we could also have a point that is a saddle. So a saddle is something that comes like this, but at the same time like came like this. So like the saddle, like on a horse. Okay, so let's take this up here because we can see our formula. Okay, so let's actually take our partials, right? So we already have two partials, and now we need to take the, I'm gonna denote it as fxx. So what's our ffx? So our fxx in here we already have this one, so we can take it to respect to x again. That's gonna be negative 12x. Okay, and then our fyy, that's gonna be, if we see it right here, it's gonna be negative 6. Okay, so now we need our fxy. So our fxy. So remember, even if you do xyx, it doesn't matter. The order doesn't matter. So I don't know. We can choose this one. So we did in respect to x to y first, right? So now let's do in respect to x. So it's just going to be 5. And let's see if that works. You know, respect to y here, this constant. So y, yep. Okay, cool. So now we can apply this formula. For if we have to apply for the individual critical points. So let's first apply it for the 0, 0 critical point. So if we plug in 0 into here, our determinant, right? We will have our fx, our fx is going to be 0 times 0 because, yep, yeah, because we're going to plug a 0 here. It's going to make this 0. This is going to multiply to here to 0. That goes away. So now we have this xy. This would be a negative, well, this would be a negative 25. So we will have a negative 25. Okay, so these are the rules. If d is greater than 0 and f of x is greater than 0, then we have a minimum. So that's the first. if the determinant is greater than 0 and f(x(x) is less than 0, we have a maximum. And then if d is less than 0, then we have a saddle. And then the test, and then if d is equal to 0, then the test is inconclusive, and we cannot determine this with this test. So these are the rules. So let's look at for 0.00. So we got a negative determinant. That means this is a saddle point. See, so we can write it here. Yeah. So this is saddle. Cool. So now let's test out our, and remember, only signs matter. The actual value doesn't matter, as long as you can tell what's going to be positive and what's going to be negative. So now let's test out our second point, this weird fraction. Okay, so let's see. If we plug in 25, 36, a positive, times a negative, this is going to be a negative number. So we know for 25, 36, and 125 over 216, right? If you plug it, our f, we can first determine fxx is going to be a negative number, right? So it might be, so it's definitely not a minimum. It might be a max, or it might be a saddle, depending on what determinant says. So now our determinant for this point, for that point, we just have to plug into a formula. So fxx, that's going to be negative times another negative. So this is going to become a positive. And then we have it minus the fxy. This is going to become a 25, right? Minus 25. So okay, this is now this is the instance where we actually have to calculate it, because I don't think, well, let's think about it, So this fraction is going to be 0.7, right? It's going to be like something like that. This 125 is going to be another small fraction, like maybe 0.6, right? So like 0.6, I'm just guesstimating right now. And then, this two would get a really small fraction, right? Well, yeah, these two. And so if you multiply this 0.7, let's, we can find out the actual value. So 25 over 36, that's going to be, oh, okay, yeah, it's about 0.7. And then it's 0.6944, but it's fairly close. And then 125 over 216. Yeah, we can round it to 0.6. Yeah, maybe 0.58. So this 0.7, so negative 12 times 0.7 with negative 0.84, and then we're going to multiply it by negative 6. We're going to have 50.4, right? 50.4. So now if we subtract it, our determinant is going to be a positive number. That means this is a maximum. That means this is max. Perfect. So we have a saddle and we have a maximum in this function. So yeah, overall, this just follow that determinant function. Then next week, well, and then sorry, and then in the next video we'll be talking about absolute maximums and um, yeah, absolute maximums using the thing called the Lagrangian, and then we're finally gonna move into multiple integrals. Okay, thank you.